On that, we'll talk about
I changed the title.
modular forms, relations in a fundamental Lie algebra, these mixed elliptic motives that Dick talked about this morning, so it's related to Dick's stuff.
Right, so I changed the title to elliptic analogs Ihara Tako Schneps.
Well,
So this is what I'll actually talk about. It's you can
also related.
easiest to think about it this way as elliptic analogs. Results. I'd like to thank the organizers for asking me to inviting me to speak. It's a pleasure to be here. And I'm going to talk about some old work, so I apologize to everyone in the audience who's heard this before. And I should mention there's lots of related work, of course, by Ihara and Tako and Schneps, and with Hain and Matsumoto on universal mixed elliptic motives. Nakamura has done related work in a Galois setting. So I'm going to talk about something elliptic, and in particular some distinguished derivations on the Lie algebra and two generators. And these derivations show up in the works of many other people. So in Nakamura in a Galois setting, in Levin Rassenet and Enriquez in some Hadja Durham setting. And I think I don't really know anything about this work of Francis Brown and Levin, but I'm been told I think that this is also related, and there's some Hodge theoretic work of Terasoma, which is also related. So the plan is I'm going to first recall these results in the title, which is something that happens over P1 minus 3 points, or GM minus the identity, whichever you prefer. I'm going to talk about, and then in section 2, I'll talk about what the elliptic analog is, and I'll set this up, and I'll say what the main result is, and then in this work of Ihara and Tako, there's some congruences which show up modulo the numerators of Bernoulli numbers, and there's also an analog of that in this work, and so time permitting, I'll say something about that. Okay. Okay, so, what's that? Did you say something?
I was just saying 691.
Oh, yes. So there'll be a 691 and a 36.
Just to be concrete, you know.
And a 3617. Yeah. Okay. So section 1. Okay. So Ihara a long time ago considered the action of the Galois group of Q on the geometric fundamental group of GM minus the identity with some base point, tangential base point, say, the Atoll fundamental group. And associated with this action, there's a linearization associated with this action. And one gets, and I should say, of course, this is the profinite completion of the free group on two generators. And associated with this, there's a free Lie algebra with generators z2k plus 1, so z odd for each odd integer greater than or equal to 3. And there's a map into the derivations on the free Lie algebra on two generators, which I'll write as x, y. And so throughout this talk, actually, I'm going to use a boldface L to denote free Lie algebras on whichever stuff is inside the parentheses. So you have this action, and this is some linearized version of that. And the image of these z2k plus 1 satisfy the following. So actually, I'm going to use zk, so k is odd here. They satisfy zk of x equals 0, and zk of y is the commutator of y with some element fk. So fk here is in this free Lie algebra on x and y, and it satisfies fk equals add x to the k minus 1 applied to y plus some more terms which all have at least two y's in them. Okay. So let me write just some notation. So I'm going to write lk xy for the decreasing filtration on this free Lie algebra determined by these numbers of y's. So this is like, this means sort of ky's. So just take the two-sided ideal generated by y in the tensor algebra, so the Freely algebra sets aside the tensor algebra on x and y, so take the two-sided ideal generated by y, take its kth power, and intersect that with the Freely algebra. So that's this decrease in filtration. And now this induces a filtration on the derivation algebra. So set der k Lxy, just the induced filtration. So just remind you very briefly, this is the delta and the derivations, which shift the filtration on the Freely algebra by k. So the delta such that delta of v is in L j plus k whenever v, for all v in Lj and all j greater than or equal to 0. Okay.
You need the derivations to annihilate x bracket y?
No, I'm just recalling the what happens in a Hara situation. So they annihilate x. Just x.
Oh.
Okay. Okay, so there's a couple surprises which occur when you consider one considers this. So the first surprise is that well, this Freely algebra on the generators z2k plus 1. So this is going to, the rest of this lecture, this is going to be a Gothic k. Or,
So what's the L that you put in everywhere? I thought that was the L.
sorry, what?
You've been writing an L everywhere. Double L of xy. I thought that was the L.
L means freely.
Yeah, so this is just, yeah, let me just write that. So my convention, so this is just some notation. LV means the Freely algebra on the vector space V. Vector space V, and if I write a sequence of elements, I mean we'll take the vector space with that basis, and then that. Okay. So K.
Okay, so this K, so this we are just like if you are over constant QL, right? Because you are.
Yeah, so I haven't said.
So you are over G or over Q or over QL, which.
So I'm just over Q or over C if you want. So I haven't said. I just said that there is this Freely algebra associated, or maybe I should say related to this action, and so I am not saying exactly saying so how it comes from that. Yeah. Okay. So there's a couple surprises. So the first one is that the image of K in this derivation algebra is now known to be free, thanks to the work of, it's now known to be injective. This map is known to be injective, thanks to the work of Francis Brown. But, and when Hara was working on this, that wasn't known, but it was certainly believed to be the case. But there's some surprises in that there's still some relations, some things which look like they might be relations or in the image. So I'm going to say right now.
Map's injective.
But there are relations in the associated gradient.
Yeah, I'm about to say exactly what I mean. That's just a preamble. Okay. So the first surprise is that there's I'll tell you exactly, a relation like this. Okay, this is congruent to 0 mod this der 3. So I just defined this filtration on the derivation algebra, the Freely algebra, and so there's this relation. So this is congruent to 0 modulo der 3. Okay, so Ihara didn't normalize it this way, but later did, and so doing it this way, you'll see these we'll come back to these numbers in just a moment. So there's this surprise, and the second, and there's plenty more of these like this. And the second thing is that there's also a congruence modulo 691. And so, in fact, the same thing. You can define everything integrally, and this is this left-hand side is in fact not only 0 modulo this third step in this filtration, but it's also 0 modulo 691 this derivation algebra, at least over ZP, where Z is, where P is 691.
So the Z's are all linearly independent mod there too, is that the
Yeah. Okay. There's two surprises. Okay. Oh, and then Ihara and Tako proved the theorem about these sorts of relations. Okay. So theorem. Okay. So. There are dim-C cusp forms. Take the cusp forms for SL2Z of weight n, and so the theorem is going to be that there are that dimension number of relations like this in the particular weight. Relations of the form some a n minus k k z n minus k c k congruent to 0 modulo der 3. Okay, so sum of the k.
What is this notation Sn of the self?
The cusp forms, the cusp forms for the group of weight n. Okay, so these coefficients.
They're explicitly known in terms of period form.
That's right. That's what I'm going to have to say next. Okay, so I'm just recalling this because the results are going to be analogous. That's it. Okay. 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 So. Okay, and then so Leila Schnaps, she made this explicit via period polynomials. Okay, so I'm going to recall. I imagine everyone here, or a lot of people here, have seen period polynomials, but I'm going to recall them just to be complete. Okay. Okay, so let me say what period polynomials are. Okay, so period polynomials, let me say in words. So you take a cusp form, f, and you so f of tau, and you multiply that by the polynomial x minus tau y. So the polynomial on the variables x and y to the n minus 2 if f is weight n, and then you integrate up the that d tau up the imaginary axis. Okay. So if f is in Sn SL2Z, okay, then you set Rf of xy to be the homogeneous polynomial in the variables x and y of degree n minus 2, the integral f of tau x minus tau y to the n minus 2 d tau. Okay. Okay, and then you can write this as a sum of two terms, okay, which I've written Rf plus and Rf minus, and Rf plus, these are the terms where the degrees of x and y are both even. So this is x to the even, x even, y to the even, and these are the things that form x to the odd, y to the odd. What did you say?
Sure. The first one is called R minus, and the second is called.
So it's funny you mention that. I saw there's two different papers in which both have your name on them, and they have different.
I said in half the papers.
So I prefer
It's for the left and the right.
I prefer this one, but
The reason
yeah,
is there are two involutions.
that's right.
They're opposite on period polynomials, and so one is even and odd, and the other is symmetric and antisymmetric.
Right. So
Yes. Yeah.
So I'm justifying the the fact that I'm going to use this one because in one of the papers with your name on
Don't
it.
justify it both. Yeah.
Sorry. But no, I prefer this one because, well, we'll see in a moment. Just because the plus is sort of an even thing, and those relations there involve two zk's, and I want this is going to show up in something on the table where there's 3, and I just wanted the plus to correspond to even instead of minus. But yeah.
Yeah, but this also shifts by 1. I mean, the multiple zeta of a comma b corresponds to x to the a minus 1 times y to b minus 1.
Oh no, I meant not this. There's 2 zk's there.
Yeah.
And that 2 is going to be it's an even, and I want that even to correspond to the plus. We'll see, but whatever, doesn't matter. Okay. I'm on page 2. I'm like, okay. And so the example, you've never seen this before. So delta is the unique Hess form of weight 12. Then R delta plus of xy is proportional to minus 36 over 691 times x to the 10th minus y to the 10th plus x to the 8th y squared minus x squared y to the 8th minus 3 times x to the 6th y to the 4th minus x to the 4th y to the 6th. And R delta minus is this going to be?
That's the minus of minus. The 3 you just wrote.
What's that?
On the right, you have 3 minus signs, x to the 10th minus y to the 10th. That's why this is really the minus part. Okay, but it's fine. I mean,
Well, just change it in your head.
Wrong in the first place.
Okay. Okay. And then R delta minus is proportional to 4 x to the 9th y plus xy to the 9th minus 25 x to the 7th y cubed plus x to 3 y to the 7, sorry, plus 42 x to the 5th y to the 5th. Okay, so I'm writing these down because we'll see these numbers. So this 1 and this minus 3 is this 1 and this minus 3, which I'm about to say what Layla's result is. Okay, so and important thing I wanted to mention is that I extended the definition of RF to Eisenstein series. So this integral only converges if f is a Cuss form, so it's not. So one has to do something. So he extended the definition of RF to Eisenstein series. And REN plus or minus, but the plus being consistent with the plus that I'm using, which is wrong, is proportional to x to the n minus 2 minus y to the n minus 2. Okay. Okay, and so Layla proved the following result, that sum a k n minus k of zk zn minus k is congruent to 0 mod dir 3 if and only if these coefficients come from a period polynomial.
You come from where?
What's that?
Coefficients come from where?
A period polynomial. I'm about to, yeah, that's right. If and only if a n minus k, k, x to the k minus 1, y to the n minus k minus 1. I'm just subtracting 1 and making it anti-symmetric. Y to the k minus 1. If and only if this, so for some k between, so k and n minus k each between, so what do I want to say here? 3 less than equal to k less than equal to n minus 3. If and only if this is RF plus of xy for some f in modular form, some f modular form of weight n for SL2Z.
But you have to take away the n minus 2 degree part.
I think I did that by writing this.
Right, but RF plus minus its highest degree, its n minus 2 degree.
No,
I mean by writing the
it's correct.
by writing the just by putting these inequalities here. I just
I mean, like the 1 and the 3 or the 1 and the 3 of SK after you subtract an isolation series. That's why he explained what isolation series is. It's not a custom. So you don't have to subtract anything.
yeah. So I've written modular forms here, but there's only the mention of cusp forms,
Okay.
such things, because I've,
Okay.
like you said, removed the endpoints. Just for okay. Okay. So now that was what I wanted to recall about this work of Harataka and like Schnaps. So here in this elliptic analog, so instead of thinking about gm minus 1 inside gm over spec q and an associated action of the tall fundamental group of this on the geometric fundamental group of that, and linearization. Instead of this, the analog, which we heard in Haynes' talk this morning, is the following, or an analog is the following. So I'm going to use the notation that he introduced. So on the bottom here, I've got this M1 vector 1, which means the moduli of elliptic curves plus a non-zero tangent vector at the at 0. Okay, and over that sits the universal elliptic curve E, which I've written script E here, and I've removed the identity section right here. Okay, so consider this. So I'll just so let me not write out the definition because we heard it this morning. But the moduli of elliptic curves plus a non-zero tangent vector at 0. Okay. Okay. So here, you can the take curve gives you a tangential base point here, and one gets the following. So take this M1 vector 1 with a tangent vector associated to the take curve. Tangential base point, sorry, associated to the take curve. And this acts on the geometric fundamental group of some fiber, say over the point tau. Okay, with so tau is a point of this, actually, not the. Okay, so you have this action, and there's again a linearized version of this, which I'm not saying exactly where it comes from, but the linearized version of this, which analogous to what happened in the P1 minus 3 points case, is the following. So this notation I'll continue to use. H is the standard representation of the Lie algebra SL2. Okay, so take its 2 symmetric power, okay, and take the free Lie algebra on that, and then take again this K, which is the free Lie algebra on this Z odd greater than or equal to 3, and there's a map into the derivations on the Freely algebra of this H. Okay? And furthermore, so this is this
K is the same sort of one.
K is the thing that's this is K is this will always be K. So Z K plus. Okay, so H is a representation of SL2. This is, of course, a representation of SL2. Give K, think of K as a trivial representation. Sorry, this is too small. Think of K as a trivial representation of SL2. Trivial. Okay, and this map is SL2 equivariant. So this is SL2 equivariant map. And I'm going to call it capital Phi. Okay, and so just to keep things, what do I want to say? Maybe to help your push.
So when you say it's a standard representation, so there's an X and a Y. Are they the same? Presumably the same X and Y as you had before on the K part? Or
Not exactly. I'm gonna.
Because the other was if they're symmetrical. I mean, one of the derivations.
Right. I'm actually gonna use it. So yeah. So.
No, I'm asking if that X and Y has any natural SL2 structure. That's just a separate X and Y. One way before.
Does it have a natural? Yes. Right. I don't want to.
Okay.
I'm not exactly sure.
What was the question?
Let me not get. The question was just, well, yeah. Let's come back to it at the end. And I'm going to use actually a basis called A and B. I'm going to write A and B for my basis of H, where A is going to be the highest state vector. So I'm picking a Carton. Okay. And oh yeah. So just to, in case you're wondering, why these two things here, or sort of what these things have to do with, you have the following short exact sequence of Étale fundamental groups. The geometric one. And so these two things, the K part is just coming from this part, and this part here is just associated to this purely geometric stuff. Okay. So this is sort of associated to that, and this is associated to that. Okay, and furthermore, and this this choice of tangential base point splits this, gives a section of this short exact sequence, and the image of K inside these derivations normalizes the image of this thing. Okay, so okay, so this is very what do I say? So I learned this from Descartes. I meant to mention at the beginning. So the whole content of this talk was, the theorem of this talk was the content of my my undergraduate thesis at Duke under his direction. So all of this is thanks to him.
So can we deduce from this last short exact sequence that you wrote down that pi 1 of MTM, the original, acts on that L of sim 2MH? That's the L of Z3, Z5 that you had before.
Is that correct?
Sorry, didn't hear the question. Can you
Yeah. No. Sorry. It's the. I didn't write it down. I just said it in words. I should have written it down. Phi of k acts on phi of this other thing. Sum to the 2m.
Right, that was my question.
Yeah, but not absolutely. So in fact, the whole content of this talk is going to be about the kernel of phi restricted to this. So it has a big kernel, and that kernel is, as is predicted by Hein and Matsumoto, that kernel can be described by cusp forms, and you need to mod out before you get an action.
Can you explain a bit how you pass from the pi1 of the geometric version of M11? I mean, that pi1 is exactly the Bray group on 3 strands. It's just isomorphically Bray group.
Right. So yeah, I really.
And how do you pass from this sim?
So I mean, so the way I think about it, that I learned from Dick Hein, is that he has him and Matsumoto have this notion of weighted completion,
Yeah.
and so I think about these things as coming from this thing here as coming from the weighted completion of this guy with respect to the monodromy on the standard local system over M1, and so, but I think it'd probably be best if some of the experts that actually answered your question have gone down. Okay. 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 And
How
so,
this action looks? I mean,
what's that?
can you say how this action looks?
I have no idea how.
I mean, the original one, defined. How is it defined? So.
I'm about to say where the stuff
How
on.
it's defined. In the old one, you told us more or less the form. You said that you have to drift on x and y with some
Yeah.
polynomial. Can you say something similar, just roughly the form?
Yeah, I'm about to.
Oh, you're
But
about-
yeah. So I have no idea about 5k, but I will say 5 the first part. And so if you take sim to the 2mh, consider the highest weight vector here, okay, and then this maps to a derivation, which I'm going to write as epsilon 2m plus 2, okay, and inside the derivations on the Healy algebra in H, I'm about to tell you exactly what epsilon 2m plus 2 is, and this is just something that Hein and Matsumoto computed. Where epsilon 2m plus 2 is a unique derivation satisfying I don't leave myself enough space. I guess I can keep it over here. This is throughout the whole talk. Epsilon 2m plus 2 of the commutator of A and B. So remember, A and B are my chosen basis for H. Epsilon of that is 0. So that's epsilon 2m plus 2 of A is add A to the 2m plus 2 applied to B. So just 2m plus 2 successive commutators, and it's homogeneous degree 2m plus 2 homogeneous degree 2m plus 2 as a derivation. Okay, so once you know derivation on the Freely algebra annihilates the commutator of A and B, you really only have to say what it does on A, as long as you're sort of in positive, as long as you're in degree bigger than 2 or something, or maybe 1. Okay. So epsilon at 2m plus 2 is this unique derivation. Okay, and so from this prescription you could deduce what how it acts on B, and the formula is not as simple as this, but still very simple. Okay.
S with
And then I said, sorry, and it's SL2.
wave vector.
It's SL2 equivariant. So phi is SL2 equivariant.
Oh, I see. Yeah.
Sorry, yeah. And then, like I said, I essentially have no idea what the image of K is. Okay.
But how's it even defined? I mean, have you told us why it's defined, or is that
No.
follow from? I mean, even why it's defined?
No.
Have you told us why that K is there at all? Oh, the K is there just because it's here.
Yeah, I just really, I was really hoping to to avoid trying to explain that and just let the experts tell you after. Okay. 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 So Hina Matsumoto, their theory of universal mixed elliptic motives. So these are universal in the sense that they live over the moduli space. Predicts Lie algebra relations and the image of phi in phi coming from cusp forms. And so, i.e., cusp forms give elements of the kernel of phi restricted to just this sort of geometric part. I'm going to write L geom for, so I don't have to keep writing this out every time. L geom to freely algebra on these even symmetric powers with a standard representation. Okay, and so the result that I'm going to describe is an explicit description of elements of this kernel in terms of period polynomials. And so we'll see both the even and odd, or odd and even parts of the period polynomials appear. So I actually should have said predicts an infinite family. So cusp forms give infinite families of Lie algebra relations. Okay, so let me.
Each cusp form gives an infinite.
Each cusp form gives an infinite family of relations. Exactly.
Can I just make an inspirational remark answering Don's question? Why that whole thing is going to dare elevate?
Please.
Just as pi1 of MTM acts on the fundamental Lie algebra of P1 minus 3 points, Lie of xy, this, what he's got here, this L of sim plus k, is pi1 of MEM that Dick defined this morning, and it's acting on the fundamental Lie algebra of an elliptic curve. It's the same situation exactly, which is a mixed elliptic motive. So L of h is to be identified with the fundamental Lie algebra of an elliptic curve, which is also free and two-generated.
Okay, so I'm just going to write some examples of some relations. So there's one relation like this. Okay, there's also, so this relation, let me call this, for obvious reasons, this is going to be called a depth 2 relation, depth 2 because there's 2 epsilons.
Epsilon 2 in the first bracket.
What's that?
The first one looks maybe epsilon 2.
It just,
Should be two.
No.
this is correct. Oh, I see.
It's 8 6.
Oh, thank you. Thank you.
Oh,
Yeah, it's,
wow.
yeah.
Oh, yeah, different things.
So epsilon 10 generates a copy of s to the, I should say, so this generates a copy of the 8th symmetric power, and this generates, epsilon 4 generates a copy of the 2nd symmetric power. So you might wonder why I'm calling them
There's
10
something
4.
really strange what you say. I mean, you say cos forms. I don't think you mean cos forms, you mean period polynomials. There's,
You're right. You're absolutely right. Let me
well, in a sense, in my paper with Conan, we did actually write down cos forms with period polynomials are these rational things like 1 or 3. But here there's an important proportional. I mean,
You're- yeah.
else is some transcendental.
Right.
It's really just the period polynomials.
Okay.
Just the period polynomials.
Or maybe it's these rational.
Just the period polynomials.
Well, I mean, there aren't, I say, cos forms that have them canonically.
Yeah, I'm not exactly sure what they're.
They're not defined over here.
I'll change that.
Conan and I wrote down the actual cos forms that these period polynomials are these rational things.
Right.
Right. So I'm
But it's
actually sort of working over. I've written Q here, but I guess I'm really working over C. It doesn't.
No, but the relations are over Q. I mean,
Yeah.
it's very strange to multiply this by transcendental number. The
Yeah.
relation, it's a perfectly good relation over Z. So,
Yeah, you're right. But yeah. Okay. Okay. So there's a more interesting one. Okay. So it's a more interesting one. This will take me a moment to write down. Should have written this down beforehand. Oh, I haven't said what epsilon naught is. Where do I want to write that? So let me just write somewhere that epsilon naught is the derivation which sends a to b and b to 0. Okay, and so the image of phi on this geometric part is spanned by the epsilon 2. This is generated by the epsilon 2 plus 2 plus plus the action of epsilon naught on these. So epsilon naught is the like a lowering operator for SL2, and so phi of LGOM is generated by these and epsilon naught. Sorry, this is just okay. So this over 2 plus, hopefully I copied this correctly, epsilon 12, epsilon 0, over 10, minus 25. This is, well, once I'm done writing, the whole thing is going to be 0. Epsilon 10, so it would be a relation. Epsilon 6, epsilon 0, over 4, plus epsilon 6, epsilon 10, epsilon naught, over 8. Don't worry about these things in the denominator. This, the natural. I'll tell you in a second. Okay, so minus 231 over 20, epsilon 4, epsilon 4, epsilon 8, minus 345 over 8, epsilon 6, epsilon 6, epsilon 4. Okay, now I'm done. Okay, so each thing in parentheses is a highest weight vector for the action of SL2, and so that's why these two things are grouped together so as to make it a highest weight vector, and these 2 and 10 and 4 and 8 are just the natural, sort of the natural things to make this sort of well. Anyway, there's a natural normalization, and these are them, and so of course.
Is this a fact or a prediction?
This is a fact.
You use the word prediction.
This is a fact. This is equal to 0.
But in general, these relations are only predicted, or these are
That's right. Yeah, I'll say the result shortly, but yeah.
Excuse me, is it supposed to be encoding something at triple sums of weights 19? Am I counting things up right?
So if you want to
19.
if you want to go figure out what the if you want to say, to do the indices right in your head, just remember that epsilon 2m plus 2 generates a copy of s to the 2m. And so this is like,
This has no analog in the world of multiple effects.
Thank you.
oh,
Francis has given me the.
okay.
But you didn't mention multiple sequence in your question, so it's hard to
It's
guess.
a triple sum.
There are many sums of things
This
in
is a
mathematics
fact.
that aren't multiple.
Oh, would I have 10 minutes left? Okay.
That was the previous bullet.
Where did these numbers come from? I mean, the last two?
I have no idea.
The answer to my question.
This is a fact which can be, I mean, I checked 5 mathematics.
Sure, but I mean, the first coefficients up to those funny denominators are what we've seen.
That's right. I have no idea where the other
The
coefficients
others, so there's
No idea.
Not even a prediction.
But
They're not even well
Not to
defined,
me.
though.
they look like a little bit like 1/3 and 1/2 of 691. I can't resist noticing.
But they're not well defined.
That's right. So they're not. That's right. They're not entirely.
No, but
What do you mean they're not well defined?
So
Got quadratic relations, so you can write the triple brackets in many different ways.
anything, but if it was
And you make it come up with, you're right, the 691 is practically staring you in the face though.
yeah, but it's
Twice.
funny, isn't it? Doesn't mean much. I don't know.
It's hard to imagine it's a coincidence.
okay. So
This gets you.
so theorem.
Sorry about that, I'm sorry.
Let me just not even write theorem 1. So theorem 1 was that. I guess I should write it. So theorem 1, and this is almost exactly the same result as Layla's. Epsilon v equals 0, e plus v equals k plus 2, if and only if the sum a u v x to the u minus 2 y to the v minus 2 minus x to the v minus 2 y to the u minus 2 e plus v equals k plus 2. So if and only if this equals rf plus of xy for some f and mk SL2C. Okay. So this is actually pretty easy. Okay. And so theorem 2 it won't be nearly as strong. So let me say, so theorem 2, so roughly, I guess looks like I'm not going to get time to make a precise statement, but, or maybe I'll just do that after this. Okay. So if you have a depth 3 relation, so that would be something of this form. So I should have said these, everything here is graded by depth. And so, even though I haven't precisely told you what it is, but this is a depth 3 relation. So if you have a depth 3 relation, so then, and so also I mean by a depth 3 relation, I mean an expression of this form, which is a highest weight vector. So I should say maybe a depth 3 highest weight relation, then the coefficients of the terms with 1 epsilon naught in them come from
With one?
epsilon naught. So these terms here, these terms all have 1 epsilon naught, which is the coefficient you understand, and these ones, or that I understand, these ones I have no idea. Then the coefficients of the terms with 1 epsilon naught come from RF minus of xy for some cos form f, some f in for some cos form.
Now the weight has gone down by 4 from the sum of the weights.
That's right. Yeah. But yeah, like I said, though, if you perhaps this is a poor choice of normalization, but it's useful to have epsilon not be here. So anyway, the way to keep track is just that epsilon 2m plus 2 generates a copy of the 2mth symmetric power, and so then just add the symmetric, just add the so 2 plus 2 plus 6 is 10, and so cos form is weight 12. Okay, so this is theorem 2, and then if I understand correctly, we'll hear about a significant strengthening of this in Layla's talk in the next couple days. Okay.
But didn't you prove something stronger? Namely that modulo a certain,
That's right.
modulo a certain filtration
Yeah.
in a cubic relation
Yeah.
for every.
So it looks like I'm not going to have time to state that result, but so this is theorem 2, and then so this theorem,
But is the converse also true? Here, I mean, so no,
converse being
well, that if you start with the cos form, that such a relation exists to multiple terms that don't involve it. I mean, in other words, you get every cos form.
that's a good question.
This is
I-
this is something that we just proved recently. So yes, it is true. That
But
I'll
it's
talk
not
about
part
that
of your
in a
theorem.
minute.
So you,
It's certainly not part of my theorem. I'm unclear of on which. Yeah,
So in this paper, he actually asked the question. You know, does every beginning like this lift to a real?
that's right. So this is definitely not if and only if. And then theorem 3 is just, in fact, so this theorem 2 I can generalize to any depth, but it's still pretty weak. So this you can generalize to any depth where the terms with one epsilon naught becomes the terms with the most possible epsilon naughts. That's any depth, and so one epsilon naught goes to the most possible. So this is a very small subset of the coefficients of a relation. Most possible.
Most possible is d minus 2, right?
it's
Yes.
well, there has to be 2 left over if you
Right.
get a
It's
cos
d
form.
minus 2.
So one epsilon naught goes to the most possible epsilon naughts, and as the depth when the depth is even, you see the r plus, and when the depth is odd, you see the r minus. So that was all. That was the reason at the beginning where I wanted plus to correspond to just so the plus matched up with even.
But
Yeah.
if we call them W even and W odd, it would also work. Even would correspond to even and odd.
Oh, if I called r minus r.
Yeah, I mean, I still use that.
Yeah,
I call it even and odd. And
I see. Oh yeah. Okay. I can change that. Okay. Okay. So let me say very briefly how one proves these sorts of results. So the proof is actually entirely elementary. Well, it's elementary modulo the work of other people who have characterized the exact image of the period polynomials. So I believe it's due to Eichler-Schmurr. Is that correct? Eichler-Schmurr characterized the image of these. Is that?
Dog maybe and plus money. I'm not quite sure.
Oh, okay.
Well,
So
always says all 3 names just to be safe.
yeah. So Eichler-Schmurr, and Menin. So the proof of these threats is very elementary.
And also,
using
really strict period polynomials. Once again, if you actually talk about cos forms, then there's one mystery which is in the space of even period polynomials, which is the space you're using. You have the image.
So sorry, by even you mean r minus?
No, even. Everybody knows what even is.
Okay.
Even is even. Okay,
But I mean-
but let me finish the
That's
sentence.
right.
In the space of even polynomials, for instance, for weight 12, there are 2 of them. X to the 10 minus y to the 10, and the one you wrote down. So the other one, the x to the 10 minus y to the 10, it's Eisenstein. Nobody disputes that. But how do you know which one is the cos forms? And the way you've said it, that would play a role. Although it doesn't. That's actually their Conan in mind. So actually knowing what the cos forms give you,
Right.
it's a more detailed thing that I'm sure you don't need, that nobody cares, but it's part of it.
So actually, I won't have time, but so in depth 4, I don't have. Again, I just have this sort of weak result, but it turns out so computer calculations you see a depth 4 relation, and there you actually see the 36 over
Oh, you get the
691.
36 over
You
691.
actually see it, and you don't see something like this. You don't see just the
I
Eisenstein.
see.
You actually see that.
Depth
But I have no.
Oh, that's very interesting.
I have no.
Conjecture for depth 4.
That's just computer calculation. I have
That's
no-
just where.
yeah.
Okay, well then you would need, so that thing is determined by the theorem of Conan.
Right.
Except that the images of actual customers.
Yeah, but I can't prove anything like that, and the only thing I use in the proof is the thing, the easier thing. Yeah. Oh, so anyway, so I just have a couple minutes left. So the way one proves this is, like I said, it's very elementary, and all you do is you evaluate these derivations on the generator A. So once you know, so all of these things in all of these derivations like this, they all annihilate the commutator of A and B. And so to understand whether a derivation is 0, you just have to evaluate it on A. And so what one does is evaluate the derivations on A, and you just sort of see what you get, and what you get you can sort of write very explicitly in terms of a period polynomial looking thing. So this would be clear if I just write something down. So let me just give, in the last minute, where is this? Somewhere. Just to take out any possible mystery. I don't know where I've written this. Okay. So let me just, for example, explain the proof of the easiest theorem, which is theorem 1. So you evaluate, say, epsilon, the commutator epsilon p, epsilon q on the element A, and you can write this, you just do the computation, and you can write this as some combination, some coefficients lambda ij, I didn't leave myself enough space, I'm sorry. Lambda ij, add a to the I of b, add a to the j of b. So this lives in the Lie algebra. Consider that in the tensor algebra on a and b, and you can write it uniquely in this form: add a to the I applied to b times, there's a multiplication in the tensor algebra, add a to the j of b with some coefficients lambda ij. And then to this expression, you just associate to this expression the polynomial lambda ij x to the I y to the j. And when you do the computation, which is again quite easy, you get so you find so one finds that this polynomial, let me call it whatever, it's p, even though p appears twice here. One finds p equals some constant times the polynomial x times y times x plus y, this is just some stupid thing, times x to the p minus 2 y to the q minus 2 minus x to the q minus 2 y to the p minus 2 times the important part, which I'm about to write. Not a sum. So minus, ran out of space again. Star equals minus the identity plus t. I'm about to define these things. So T is the matrix 1, 1, the upper triangular matrix, T prime.
You don't want to add these, you want to multiply. The xy times x plus y.
Oh, yes, thank you. I'm sorry.
That's surely not the
Yeah, of course. Yeah, of course. Thanks. Okay. So there's a SL2Z acts on, say, x and y on the left, inducing a right action on the, so there's a right action, natural right action of SL2Z on polynomials, homogeneous polynomials. And so this is just that right action of this element. And you just compute, and you see this. And then And then, as I learned actually in the paper of Gengo, Kaneko, and Zagie, you can use this expression right here to characterize period polynomials. So the period polynomials are exactly the kernel of this map, and so in this case here, some linear combination of these derivations are 0 with some coefficients, say beta pq, if and only if when you multiply this by beta pq and sum over p and q, you get 0. So if and only if this original thing was a period polynomial, and so that's how one proves this first theorem. And then the more general thing is the idea is exactly the same, it's just that the computations become more difficult. So that's how it works.
Do you have something like this that characterizes the one weight 12 cusp form with minus 36 over 691?
Not in depth 2. In depth 2, it's sort of odd, or it's sort of weird, unusual.
But is
I
there
don't
a maybe I should ask John that. Is there a characterization like this, but that picks out the one cusp form among period polynomials?
What do you mean the one?
Oh yeah.
One with minus 36 over 3.
Yeah.
What do you mean in weight 12?
Yeah, in weight 12, for
Well,
instance.
in general, yeah, no, that's what I said. The theorem of coordinate group picks out the period polynomials of cusp forms in the space of even period polynomials. So it's called dimension 1, and it gives a complete answer. Yeah.
So can we have a reference?
Coordinates like here, we have one paper. Well, no, we have two papers, but it's one.
Yeah.
It's called rational periods. Just go to my webpage.
It's at least 3 people have already showed me this, but it hasn't sunk in yet.
Well, it will. It will.
Yeah, it will.
So that's it.
Maybe today's the day. So, apart from me, are there any other questions?
Well,
Should we thank the
no,
speaker?
no. I had a remark, which was that it was a wonderful talk, and a question, which is it's a suggestion. I have a guess where these numbers might come from, the 231,
Oh, that's
345, except that Fran said they're not. No, don't.
Oh, sorry. I was gonna. Yeah, you're right. Everyone can
You
say it
said they're
better.
not unique in general. I mean,
So-
even in cubic
The
case.
Theorem modular from ideal because
No, but even in the.
But
in
it-
that particular case, weight 12, whatever, it happens to be.
So
Yeah, so
let me
what-
say, so these ones are.
Let me say what my guess could be for the coefficients.
Yes.
So the coefficients 4, 25, and 42 are the coefficients of the period polynomial, and it's very well known up to some binomial coefficients, all kinds of normalizations. The coefficients of the period polynomial of the cusp form are the same as the values of its L series at the center of the vertical string. But by the Rankin-Selberg thing and an extension that was given by Rankin and by me, that's the same as the cusp product, as the Petersen-Taylor product of that cusp form, say delta with product of 2 Eisenstein series. Or equivalent, if you take the product of 2 Eisenstein series, let's say E4 times E8. In the case of E2, you have to be careful because E2 isn't a modular formula. Take E2 times E10 plus a multiple of E10 prime. And then you write that as a combination of Eisenstein plus cusp form. You pick out the coefficient of delta. That gives a number. Those are those.
Oh, wait. Yeah, I
Therefore,
missed
the
that.
guess here. So now
Say it
when you
again?
finish the sentence.
Yeah.
So now, it's the coefficients 4, 25, and 42 are what you would get if you took E4 times E8, E6 squared, or E2 times E10 with this modification, and wrote it as a combination of E12 and delta, and you pick out the coefficient of delta.
Right.
So now you can also take not 2 Eisenstein series, but 3 Eisenstein series, because
Absolutely.
weights out
Absolutely.
12,
Yeah.
multiply them out, and pick out the coefficient of delta. And it would almost surprise me if you didn't get those
Yeah,
numbers.
it's funny. I tried it back a long time ago. I tried to do that, and for some reason I was
Yeah.
much stupider than that. I couldn't do the computation. I think it. So I erased this earlier. So the work of Terasoma sort of is, like I said, I erase it. He does some Hodge theoretic computation, and so he computes some. But almost, well, yeah. So he computes some regulator of the cup product of 2 sort of Eisenstein elements.
No,
Whatever.
Based on something fancy, I'm just multiplying.
Yeah.
E4 squared times E6 or something and picking out the coefficient of delta. It's a totally trivial calculation. You can do it by the computer in 6 seconds. And it either gives, of course it's up to binomial coefficients, but that the second factor is a 23, so that's sort of a big enough round factor for you to see if you're getting the right thing. So anyway, it's worth trying.
Yeah, it's fine.
You have
Yeah.
another question?
I asked my first question, I got a very clear answer that what you were saying at depth 3 was not supposed to be touching on my concerns with multiple zeta values of depth 3. Now let me ask an even more outlandish question. As clearly what you were saying at depth 2 touches very deeply on the disappearance of irreducible multiple zeta values of depth 2 because there are relationships between them encoded here. That has to, by Don's result, produce the appearance at weight 4, because we know that something. Yeah. So, does what you say about depth 4 at all touch upon the fact that there are not enough relationships between weight 4 sums, as Don discovered 15 years ago to his surprise? In other words, one doesn't want to see something of depth 12 and weight 4. One doesn't in the alternating sums. No?
I guess.
I mean,
there are.
in an extremely subtle way.
Yes. But,
So I can explain that a little bit.
Fine. So I asked one naive question, and Francis, my sage, said no, it's not about triple sums. And I asked even more outlandish one, and he's saying maybe.
Yeah.
Thank you.
Yes.
Sorry.
Now
Yes.
no. Can you explain maybe intuition behind? So you start with cast form F, and then you construct RF, and it looks like a complete mystery to me. What do you? Is there any intuition behind it?
So let me give one answer, which is that, like Don said, like the coefficients of the let's say x to the a, y to the b are up to some factor of 2 pi I and stuff, or the values of the L function of f in the critical show, and so they're they're periods.
Also, another question. Your L geometric. Why do you call it geometric?
I called it geometric because it came purely from a geometric fundamental group, which is that pi 1 of it was associated in a way which I continued to not tell you, and I'll let the experts tell you. But I called it geometric because it was associated purely to a geometric fundamental group. Oh, by bar I mean base change to Q bar.
Which is the Bray group on 3
Which is,
strands.
yeah. So that's why I said geometric.
Any more questions? Okay.